All right, let's go through and do another example here. Instead of having a air nozzle, we now have a steam turbine. Remember, a turbine produces power, or shaft power in particular. So it works off of steam, not air. So obviously we're going to be using steam tables and saturation tables to do this particular problem. So we have a steam turbine that takes high pressure steam. The inlet is location 1, the outlet is location 2. Of course, there's a propeller or a turbine in there that's extracting shaft power. The inlet pressure is 10 megapascals. And that turns out to be 100 bar. So the inlet pressure is 100 bar. P1 is 100 bar. Very high pressure, 100 atmospheres. The inlet temperature is T1 is 450 degrees C. Probably going to find that it's superheated. So probably going to be a superheated steam once we actually go to steam tables. The inlet velocity of the steam is 80 meters per second. And the mass flow rate for the steam, m dot, is 12 kilograms per second of steam being fed into the turbine. Now, the turbine extracts some energy from the flow, and as a result, our outlet pressure falls. P2 is down to 10 kilopascals, which is 0.1 bar. So pressure falls from 100 bar down to 0.1 bar. 1,000 times pressure has gone down. And we're also told that the exit state is a saturated mix. So we have a quality of 92%. So it's a saturated mix. A superheated steam condenses down to a saturated mix primarily of saturated vapor, but there's a bit of liquid in there, and pressure falls by a factor of 1,000. The outlet velocity, VEL2, goes down to 50 meters per second. Okay? Pressure, velocity, and we'll find out enthalpy have fallen because we're extracting energy from the flow to produce shaft power or shaft work. Okay? What are we supposed to find? We're going to find the change in specific kinetic energy from the inlet to the outlet. So delta KE from the inlet to the outlet. We want to find the shaft power, W dot shaft, produced by the turbine. And presumably, I also want to know what the inlet flow area is. So this thing, some sort of a pipe here, some sort of pipe in which the steam flows in and the saturated mix flows out. I want to know what this flow area is here, A1. I want to know what that flow area is, all right? Okay, let's proceed. So the first thing I want to do is calculate analysis. First thing I want to do is calculate the change in specific kinetic energy between the inlet and the outlet. So delta KE from location 1 to location 2. So that's going to be 1/2 velocity at location 2 squared minus 1/2 velocity at location 1 squared. Let's group together the 1/2s. Factor out the 1/2, and I have velocity 2 squared minus velocity 1 squared. I have the inlet and the outlet velocities. They are 80 and 50 meters per second. So I got 1/2. The outlet is 50 and the inlet is 80. So I have 50 meters per second squared minus 80 meters per second squared. Okay, the unit on this is going to be meters squared per second squared, which is a joule per kilogram. Joule per kilogram. So these guys have units of joule per kilogram. not kilojoules, joules per kilogram. Let's see, I go through and crank that out. 50 squared minus 80 squared. So kinetic energy is falling as we go from the inlet to the outlet. Let's see here. So 50 squared minus 80 squared, divide by 2. And I get 1950, negative 1950. And that's going to have unit of joule per kilogram. Or converting that to kilojoules per kilogram, I got 1 kilojoule per 1,000 joules. The joules cancel out, and I get 1.95 kilojoule per kilogram. So I'll write that right up here. Delta KE from the inlet to the outlet is 1.95 kilojoule per kilogram. Okay, kilojoule per kilogram. There we go. That was easy. That's the easiest part of this problem. Well, yeah, definitely one of the easiest parts of the problem. All right. Okay, now I want to calculate the shaft power or power produced by this turbine. Well, first of all, let's define our system. Before we get too excited here, let me define my system here. Clearly an open system, I'm going to make the inside of my turbine the system. So the shaft is delivering shaft power by the system. It's out. It's producing work, so it's by the system. Clearly an open flow device with a single inlet at location 1 and a single outlet at location 2. Single inlet, single outlet, producing shaft work. One other little thing here. Well, we'll wait for the other little thing, okay? We'll wait for the other little thing. So let's write the energy balance. That involves shaft power. Let's write the energy balance and see if we can calculate the shaft power. So energy balance for an open system, Q dot minus W dot is equal to the time rate of change of energy within the turbine or the control volume plus the sum of M dot H plus PE plus KE summed over all outlets minus the same thing summed over all inlets. I'm not going to write it. It's the same thing, inlet, outlet. I'm getting tired of writing it, okay? Getting tired of writing it. You can write it down. M dot H plus PE plus KE, all right? Okay, let's whittle this down here. What do we do with the Q dot term, the heat transfer? It doesn't say it, but why don't we assume an adiabatic turbine? There's no way to calculate the heat transfer. I'm trying to calculate W dot. I'm going to end up with one equation and one unknown. I can't have two unknowns. So I'm going to assume Q dot is 0 or an adiabatic turbine. Adiabatic turbine. That's the first assumption I'm going to put down. So Q dot equals 0, adiabatic. Adiabatic turbine. I'm going to put some insulation around this thing. No heat transfer. Wrap it with some asbestos. Just don't breathe it, okay? Let's wrap it with an asbestos blanket. No heat transfer, all right? By the way, there's one of these over in the power plant. It's being dismantled now. It's not actually installed. The power plant is not generating any electricity at this moment. But usually, there's a turbine running over there in the power plant driving a generator, which is helping to power the lights. Okay, so there's one of these guys in the power plant, steam turbine. No heat transfer, so that's gone. Adiabatic. Now, what about the W dot term? There are three forms of work that we're dealing with here in the energy equation. Pressure power is absorbed into the enthalpy, so we don't have to worry about that. There's shaft work, electric work, and boundary work. I definitely see a shaft in this thing, so we definitely have shaft work going on. I don't see any wires. I don't see any resistors, any wires, any batteries, so there's no electric work. And I'm guessing, I'm assuming that the turbine itself is not changing shape. The casing is remaining intact, and the control volume is not changing its volume, getting bigger, being distorted. So I'm going to assume that the work is equal to, I'm going to write right here, W dot is equal to W dot shaft. Okay? No boundary, no electric work. So I'm immediately going to substitute W dot shaft. W dot shaft, all right? I'm going to neglect the change in internal energy. I'm going to assume steady state. So I can get rid of DEC VDT, get rid of that. Steady state. So get rid of the time rate of change of the energy within the control volume. I'm also going to neglect the change of potential energy of the steam as it flows in and out of the turbine. I have no way to figure out what the average height is for the inlet and the outlet steam. Okay, maybe there's no change in height. I don't know, depending on how the plumbing is done. Certainly steam is not very dense. It has a very low density. So even if there was a change in height, it would have to be very large to be comparable to the change in enthalpy or kinetic energy of the flow. So I'm going to neglect, I'm going to write delta PE from 1 to 2 equals 0. I'm going to neglect the change in potential energy of the steam as it moves through the turbine. So I'm going to cancel out these potential energy terms. Okay, cancel out the potential energy terms. Well, let's write what I got left. By the way, there's one inlet, one outlet. So the summations go away. So let me write what I have left over. Minus W dot shaft, minus sign, is equal to M dot out, which is M dot 2, H plus KE at the outlet, minus M dot H plus KE at the inlet. If I apply the mass balance to my turbine, single inlet, single outlet, single inlet, single outlet, steady state, no change in mass within my turbine. If I apply the mass balance, what's the relationship between M dot in and M dot out? M dot in and M dot out are the same. What goes in has to go out in steady state. Single inlet, single outlet. So I'm going to replace the M dot 1 and the M dot 2 with a single generic M dot. So this guy here is just M dot. If you want to prove that, you can go through the mass balance. You're going to see that. M dot 1 is equal to M dot 2. And I'm just going to call them M dot. Okay, let me group together the enthalpy term and the change in kinetic energy term, and I'll have my final version. And I'll also distribute the negative sign. How about that? W dot shaft, I'll distribute the negative sign, is negative M dot delta H. How about H2 minus H1 minus, tell you what, H2 minus H1 plus KE2 minus KE1, okay? Where this guy here, that is delta kinetic energy from 1 to 2. We've already calculated it, all right? So let's write out the final version. W dot shaft is equal to minus M dot H2 minus H1 plus delta KE from 1 to 2, okay? We've already got this. By the way, we have the mass flow too. We have the mass flow too. Okay, now we need to find the specific enthalpies at the inlet and the outlet. Define the specific enthalpies at the inlet and the outlet. Well, let's find the specific enthalpy at the inlet. H1 equals specific enthalpy of the steam evaluated at a temperature of 450 degrees C and a pressure equal to 100 bar. Let's see if we can find this temperature and pressure. Maybe we'll have to interpolate, but let's see if we can find something in the steam tables. Let's see here. Whoops. Superheated, R1, no, don't need that. H2O, 100 bar, 450 degrees C. Ooh, looks like we need to do, so here's H. We're at 450, so we have to interpolate between these two. If you go through and do a little interpolation, hopefully I have it here. I have H1 is 3240.25 kilojoules per kilogram. 3240 kilojoule per kilogram. And that's from the steam tables, and you have to interpolate. That's from the steam table B4, and you have to interpolate. B4, interp. I had to interpolate from B4, okay? That's H1. What about H2? H2 is a saturated mixture. I have a pressure P2 is equal to 0.1 bar, and a quality X2 is 92%. So we'll have to go to saturation tables. Saturation pressure table, 0.1 bar. Here is H for the saturated liquid. Here's HFG, which is the enthalpy change between the vapor and the liquid. Use the quality, you can quite easily calculate H2. I won't bore you with the calculation here, I'm just going to put the value down. Let's see here, H2 is 2393.2 kilojoule per kilogram. I'll get rid of the 0.2. 2393 kilojoule per kilogram. Okay, now I have all these specific enthalpies. Let's crank out the shaft power. Let's see here, M dot was 12 kilograms per second. H2, 2393. H1, 3240. And those both have units of kilojoule per kilogram. And then I have my delta KE from 1 to 2, which is 1 point. I should have a negative sign there. Kinetic energy falls, I just realized that. I dropped the negative sign, okay? Delta KE from 1 to 2 is negative because velocity going in is 80, velocity going out is 50 meters per second. So kinetic energy falls, so I got a negative 1.95 kilojoule per kilogram. Looks like I dropped the negative sign. So negative 1.95 kilojoule per kilogram. All the units are the same. Looks good. By the way, the kilograms cancel out with the kilogram and the m dot, and I get kilojoule per second, which is going to be a kilowatt. Kilojoule per second is going to be a kilowatt. Let's see here. So I have 2393 minus 3240 minus 1.95. I'm going to multiply that by 12. And I get 10, 18, 7.4 kilowatts. I'm going to convert that into megawatts. Let's see, a megawatt, running out of space here. 1 megawatt is equal to 1,000 kilowatts. So the kilowatts cancel, and I got to divide that by 1,000. And I get 10.18 megawatts. So the shaft work supplied by the turbine is basically 10.2 megawatts. 10.2 megawatts. That's how much power is being produced by this thing. Oh, shoot. Okay, well, at least you could see part of the screen. All I did is plugged in the specific enthalpies, cranked it out. Again, the negative sign on the delta KE. Potential energy falls as you go from the inlet to the outlet. Okay, so I forgot the negative sign there. 10.2 megawatts. That's a lot. That's a lot of power. A lot of power. A lot of light bulbs. A lot of light bulbs if you turn that into electric power. Okay, last thing we need to do is calculate the inlet flow area. Inlet flow area, A1. Inlet flow area. So we have the inlet here. So we got m dot for the steam. Okay? And of course, this inlet has some area, A1. Okay? So, m dot for the steam is going to be equal to the volume flow rate at the inlet times the density of the steam at the inlet. So V dot rho 1. Now V dot, that's equal to the velocity at the inlet times the flow area at the inlet. Okay? And density is 1 over specific volume. So this guy is 1 over specific volume at the inlet. Tables don't give you density, they give you specific volume. That's why I'm converting density into specific volume. So I have velocity 1, area 1, over specific volume at the inlet. Okay? Now the inlet area is what I want, A1. So let me solve for the inlet flow area. A1 is equal to m dot steam, or m dot, just m dot, specific volume at the inlet divided by the flow velocity at the inlet. Okay? Now I have the steam flow rate, which is just my m dot, and I have the inlet velocity, which is 80 meters per second. I don't have the specific volume at state 1 for my superheated steam. Let's see here, how might I get this? Specific volume at state 1 is specific volume for the superheated steam evaluated at 100 bar and 450 degrees. So 100 bar and 450 degrees C. I'm going to have to do some interpolation on that too. If we go to our tables, as I recall, we don't have, so let's, whoops. Let's go to the steam tables. 100 bar. And again, I don't have 350, 450. I have 440 and 480. So you have to do some interpolation here. It's going to be somewhere around 0.03 or so, 0.03 cubic meters per kilogram. Okay, do a little bit of interpolation. Do a little bit of interpolation here. I have 0.0297 cubic meters per kilogram, and that is interpolated from B5 in terp. Is it B5? And I've done it again. I'm sorry, B4. Okay, so I interpolated the specific volume. That's from B4 in terp. Interpolated. Okay. Okay, I've got everything. I've got the velocity. I've got the specific volume. Oh, let's see here. 12 kilograms per second. Again, this is just m dot. I don't know why I'm writing m dot steam. 0.0297, not 9. I don't know why I put the 7 there either. Okay, 0.0297 cubic meters per kilogram. And the inlet flow velocity is 80 meters per second. Let's see here, let's look at the units here. The seconds cancel out, meters per second and kilograms per second, that's gone. The kilogram cancels out in the mass flow and the specific volume. And one of the meters cancels out in my cubic meter per kilogram, and I get meters squared. I get meters squared. The result is 0.004 square meters. So the inlet flow area. Inlet flow area is 0.004 square meters. If we want to change this into centimeters, maybe a little bit more visualizable, there is 100 centimeters per meter. And I'm going to square the conversion, so I get meters squared and centimeters squared. The meters squared cancels out. And I get, okay, I'll move the decimal place over 4 times. 1, 2, 3, 4. So I get 40 centimeters squared, okay? 40 centimeters squared, or 0.004 square meters, okay? That's the outlet flow area. That's all I have for today, ladies and gentlemen. We'll finish up the chapter on energy. We'll introduce what's called coefficients of performance and efficiency. We'll wrap up chapter 4, and then we'll be moving on to the most troublesome part of the whole course, the second law and entropy. Get a good rest up this weekend, get your homework done, get everything else done, because now it's going to start getting nasty. It's going to be horrible. You're going to be, who knows, you might be in the hospital after this is all done. Second law on entropy tends to explode people's brains. So this stuff, pretty straightforward. I hope you're getting it. I hope you're used to the tables. I hope you can find properties for steam and air. Let's get this stuff down. Do the next homework involving the energy balance. Get it down. Then we're moving on to the second law of thermodynamics, and then entropy. Entropy. Take care, ladies and gentlemen.